In our previous video, we were looking at different types of missingness and the effect that it has on our data, and we were talking about the concerns we might have when our data are missing at random versus missing not at random, or if we've used some sort of imputation method, such as having the last observation carried forward. And then we created some plots to show what all of these data look like, progressing from the full raw data to missing at random, where we have unbiasedly deleted random observations from the data set. Missing not at random, where in our case, rather than having data missing from particular groups of participants, we had data more likely to be missing from later points in time. So these data are missing not at random with respect to time. And then we also had a data set in which we had carried the last observation forward. So from that missing not at random data, we filled in any gaps by just repeating the observation that came before it. And we could see this now gives us data at every cell, but it also significantly changes the shape of our data. And that can have some significant implications when we're actually conducting our analyses. So one of the first things we want to do is give you some code that you can adapt in your own settings to see how exactly data are missing. So at first we're going to look at data missing at random and recode this data set to create a new variable, which is missing at random underscore missing. And essentially this is just a logical code that will tell us if it has a missing value in that cell or if the value is not missing. We can then create the crosstabs to show the number of missing observations at each month. And then I just kind of transpose this matrix to show month as a column and the frequency of missing observations as a column. And then we can create a figure to actually plot this. And you can see that sort of the probability of missing does not reliably change as a function of time since admission. We're going to have a roughly comparable number of missing observations from month to month, and the probability of missing data in any given month is random. Now we can compare this to the missing not at random data set. So again, we're going to create a logical variable. And you can see again that varies between 0 and 1. So 0 is someone is not missing data, 1 is that they are missing the data. We can then use the xtabs function to look at the number of missing data points in each month. And you can see that there are no missing data points in the first 3 months, and then it builds up over time until by month 18, we don't actually have data for anyone. All right, then again, I just sort of transpose this so we can use this more effectively in our graph, where we're going to look at the month, and then we're going to plot the frequency of missing data. And now we can see here we clearly have a bias distribution where you're much more likely to be missing in latter months compared to earlier months, where we have complete data versus missing a significant amount of data. Okay, then statistically speaking, we can actually look at the effects of missingness over time. So there's a table in the handout that you've been provided that helps summarize these effects. So I would encourage you to refer to that table, but we're also going to look at it in these statistical models here. So first we'll go through and complete each of our models. We'll create a model with the complete data set, a model with the missing at random data, a model with the missing not at random data, and a model with the last observation carried forward. And then we can generate a summary of each of these models in order to compare them. And I'll actually pull up, rather than looking at the individual summaries from the statistical models, I'll pull up the worksheet that has the table in which we've extracted the key variables from this information. Okay, so here we have the handout from session 3. Let's go ahead and resize this. And we can scroll down to where we've actually synthesized this information in a table. So first, we'll look at the number of observations in each one, right? So for our complete data set, where we have 40 subjects, we have 40 subjects in all of our data sets. In terms of a number of observations, we have 720 because there's 18 observations by 40 people. And you can see how that gets reduced for missing at random and missing not at random. Both are missing about 60% of the data. And then for the last observation carried forward, we're back up to the full amount because obviously we've imputed a value for every missing field. Importantly, we can also take a look at the deviance in the AIC, and this should reinforce why it's important that we can only really use these model comparison statistics for data sets of the same size. Because anytime we reduce the amount of data, the deviance in the AIC will also go down by default. Because if the deviance is based on the sum of errors, if we have fewer errors to work with, that sum is likely going to be smaller by default. So again, this is an important lesson that you can only really compare models that are based on the same data set to make a meaningful comparison of the deviance and the AIC. All right, but then let's actually look at what's happening in our estimates of the individual betas and their standard errors. So specifically, we're looking at the effect of time and the linear, the quadratic, and the cubic effect. And we want to see what's happening when we have complete data. And this is essentially the truth. We're sort of assuming that this is what the data would have looked like if we could have measured everyone at each time. Then this would be sort of the unknowable reality if we were actually conducting a study. And we can compare that to missing at random and missing not at random, which is what we might be more likely to see if we were conducting a study, right? Because we're not going to get everybody at each time. People will go missing for different reasons. In a clinical setting, we're more likely to see the missing not at random case because we'll probably lose more observations as people go into outpatient therapy or just as an experiment continues. There's going to be some participant attrition due to a number of different factors. And then we can also look at our last observation carried forward. And in your handout, you'll see the betas and the standard errors for each of these different models for all three of the effects of time. The nicest way to summarize that, though, I think, is we can actually look at the betas and the standard errors as a proportion of what they are in the complete data set. So again, if we treat the complete data set as sort of the unknowable truth, looking at these other data sets as a proportion of the complete data set tells us how much bias there is in our models as they deviate away from the complete data set, and how much uncertainty there is in our models as the standard errors deviate away from the standard errors in the complete data set. So let's start with the missing at random case, and you can see that the betas are relatively unbiased. Proportionally, they're about the same. They're very slightly bigger than what they were in the complete data set, just by chance. But they're pretty close to 1, right? Indicating that these betas are about the same size as what we had in the complete data set. However, their standard errors are between 40 and 50% larger, right? So our uncertainty has increased because standard errors have gotten bigger because we have fewer data points. Now, therefore we have a relatively unbiased but uncertain distribution of effects for the missing at random data. For the missing not at random data, we can see that the betas actually start to get bigger, right? So they're increasing on the order of 15 to 60% compared to the complete data set. But as the bias increases, as we get more likely to overestimate the cubic effect, our uncertainty also increases a lot as well. So you can see that now we're actually going up by about 2.35 for the standard error. So we're very uncertain about this effect, even though it is biased. So that could potentially sort of temper our judgments. We wouldn't say, oh, well, this beta, this 42.07 for the cubic effect of time in the missing not at random data set is a great estimate of the true effect because the standard error has gone up so much. Right, so when that standard error has increased by that amount, the confidence interval gets bigger. So that's not great. Obviously, we don't want to have biased estimates, but if we are going to have estimates be more biased, we don't want to have fake certainty underlying those estimates, and we don't want to think that effects are reliably bigger or smaller than they actually are. So we can then compare the missing not at random data to the last observation carried forward, right, where we've interpolated any missing values with the observation that came before it. You can see for the linear effect of time, we're doing pretty well, but bias actually grows as we go up to the higher order effects of time, just as it did with the missing not at random data. Now we go up from about a 20% increase to a 40% increase, and you can compare that also then to the standard error. With the missing not at random, we said there was sort of a trade-off where bias was increasing, but so too was uncertainty. With the last observation carried forward, bias is increasing, but uncertainty is not increasing to the same degree, right? The uncertainty is actually smaller than the missing at random data. So that's one of the potential concerns about the last observation carried forward as a method of imputation, because it has the potential to bias your results while spuriously increasing your certainty in what your estimates actually are. So I hope that helps you understand the effects that missingness can have on your data. And we've given you some tools for being able to look at the relationship between missingness and time. You can also look at the relationship between missingness and group membership. And you also want to be really careful in terms of how you're imputing your data. There might be times in which an imputation method is relatively well validated, and you might say then, well, that increased certainty that comes from imputing is acceptable because previous data has shown that this is a valid way of doing this. But if you're just using a method to fill in missing cases and you don't really have a good empirical reason for that imputation, you might be spuriously increasing your certainty in your results while at the same time introducing bias into your data depending on what the underlying shape of your data are and where data are missing in that data set.